Welcome to this lecture on EE557. In the last lecture, we have seen the concepts of open loop control and closed loop control on stochastic systems, and we compared them in terms of their performance, their generality, or their advantage. And we have seen that closed loop control would be definitely better for stochastic systems. And in the deterministic systems, we have seen that these two control types would be more or less equivalent. In the current lecture, we are going to see the so-called transition PDFs and also the property of Markovianness. Let us write transition PDFs and Markov property. So in the earlier lectures, we have seen the concept of transition function, and transition PDF is something different, but the concepts in some way are similar. So transition PDF is the generalization of the idea of transition function into stochastic systems. And now that is what we are going to learn. So the first thing that I'm going to do is to consider a deterministic system here. And then there I will write some properties of the system equations or the state. So how we can predict the future state values given the current state and some input values. And then I will try to generalize that idea to the stochastic systems. So the first thing, therefore, is to write the deterministic system. So I have xk plus 1 is equal to fk xk uk here. This is a deterministic system. I will choose the input deterministically, and this is going to be my, or I can choose the input as a feedback of the output, but we know that it won't matter, okay? Because the closed loop control and open loop control are equivalent for deterministic systems. So I can, without loss of generality, I can think that I choose these inputs deterministically. It really doesn't matter. So now I will look at xk plus 2. We know that this is fk plus 1, xk plus 1. So I have uk plus 1 plus, and that is all. And instead of xk plus 1, I can write this upper relationship. So I have fk plus 1. It is fk xk uk, and I would have uk plus 1 here. So you see that I can actually calculate what xk plus 2 if I know xk and the inputs uk and uk plus 1. Remember that we continued in this fashion, and then we obtained the so-called transition function. So when I continue with this logic, I can actually continue with this logic by actually obtaining f functions inside each other. And we know that I can actually write x of k plus 1 as the transition function, which are the composition of these functions. And I would have, this is the transition function from k to k plus m. And this is going to be a function of xk. And I would have the input terms here, u from uk. And I would have k plus m minus 1. Okay? And we know that this is my transition function. So here we see something important. For a deterministic system, when I know xk, state at some time, and the inputs from uk to uk plus m minus 1, then because I know this transition function, I know what xk plus m is. Okay? I know perfectly what xk plus m is if I know these quantities. That is the first property that we observe in a deterministic system. So we know xk plus m if we know xk and the additional input values from uk to uk plus m minus 1. Okay? So the second thing, the second property is more or less obvious for a deterministic system. Okay? If I know xk and these inputs, in addition to these, if I know the previous states and previous inputs, nothing will change. Okay? So if in addition to this xk and this uk to k plus m minus 1, if I know the previous states and previous inputs, nothing will change in my knowledge of xk plus m. Because with only this state and these inputs, I know xk plus m perfectly. And knowledge of previous states or previous inputs will not change or will not increase my perfect knowledge. It cannot increase anymore. I know what xk plus m is perfectly. So here, that is a more or less obvious property. Let us try to write this. When we know xk and uk to k plus m minus 1, the knowledge of the previous states, the knowledge of the previous states, what are the previous states? I know xk. The previous states are x0 to k minus 1. Okay? And previous inputs, u0 to k minus 1, are not necessary for knowing xk plus m. Okay? By knowing only this, I know xk plus m perfectly. So if I know, in addition to these quantities, if I know the previous states and if I know the previous inputs, nothing is going to change in my knowledge about xk plus m, because I already know xk plus m perfectly. So now I would like to generalize this type of idea to stochastic systems. But it is not really straightforward directly, because in a deterministic system, I can talk about knowing a state vector perfectly. Okay? But in a stochastic system, there are some noise sources, and they would actually cause me not to be able to know the state perfectly in some way. So due to the existence of noises in a stochastic system, we can never talk about knowing a state value perfectly. Okay? So then how can we generalize this type of idea to a stochastic system? Let me first talk about what comes to mind. So if I write the stochastic system dynamics, then this is going to be fk, xk, uk, and I would have wk. uk here can be selected in a feedback loop, and wk is my process noise. We know that I can continue with this logic as I did in the deterministic system. So I can write xk plus 2, fk plus 1. Instead of xk plus 1, I write this, fk, xk, uk, wk. And I add uk plus 1 and wk plus 1. Okay? And you know that I can continue with this logic to obtain these transition functions. So I can write xk plus m is equal to the transition function from k to k plus m. This is going to be a function of xk, u from k to k plus m minus 1, and w from k to k plus m minus 1. Okay? So this is a transition function. All right? So now here I can say the same thing. So we know xk plus m if we know xk uk given u from k to k plus m minus 1 and w from k to k plus m minus 1. Okay? But there is a problem here. So here I have written a statement, and I told you that I know xk plus m if I know these quantities. Yes, this statement is not wrong. It is correct, but somehow it is not sufficient for us. And the reason for this is that although I can know what this state is, suppose that I know this, I can know what these inputs are. I know what input I give to the system by looking at the output. This process noise is never known. So I never know the process noise sequence in a stochastic system. So then, although this statement is correct, it is useless for us in some way. I would like to come up with a generalization of this idea. So how can I talk about knowing xk plus m by knowing only xk and u from k to k plus m minus 1? I really would not like to put here the process noise, because the knowledge of process noise is really an unrealistic wish here for us. Okay, so we cannot really know the process noise anytime. So that means that although this statement is correct, it is inachievable somehow, because the knowledge of this process noise is not really available to us. So now I'm going to ask some questions. So suppose that I remove this unrealistic quantity from here. So can I know xk plus m if I know only xk and these inputs? So can I write the same thing as the deterministic system for a stochastic system by removing this process noise from this set of known quantities? Okay? So here the answer is actually to this question would be no, because in that case I wouldn't know what the process noise is. Therefore, in this function, there would be xk, these inputs, and if I don't know this process noise sequence, I will never be able to know exactly what xk plus m is. Okay? So if I try to write the same statement as a deterministic system for the stochastic system, I'm going to remove this knowledge here, and I see from this expression that if I don't know this, I will never be able to exactly know xk plus m by knowing only these two quantities, xk and x from k to k plus m minus 1, due to the unknown process noise. Okay, so that would be also an unrealistic desire to know xk plus m exactly. Okay, so let us write this question and its answer. Can we know xk plus m if we only know xk and u from k to k plus m minus 1? And the answer to this question is no, because if I don't know the process noise, then I won't be able to use this function, and we'll be able to calculate xk plus m exactly. Okay? The answer to this question is no. So what can how can I define what is the counterpart of knowing xk plus m in a stochastic system? So I would like to find the counterpart of knowing xk plus m in a deterministic system in a stochastic system. Okay? And that is going to be the following. If I know xk and u from k to k plus m minus 1, even though when I don't know this process noise, I can actually calculate the density function or the PDF of this xk plus m. From the densities of these noise terms, even though I don't know the exact value of this realization of the noise term, I can actually calculate the PDF of xk plus m. So I will never be able to know what the actual value of xk plus m is. But by knowing xk and u from k to k plus m minus 1, even though I don't know what these process noise terms are, what their realizations are, from the densities of these noise terms, I can actually calculate the PDF of xk plus m. Okay? So the counterpart of knowing xk plus m exactly in a deterministic system is knowing the distribution function or PDF, probability density function of xk plus m given these two pieces of information. Okay? So I will write this as a question and an answer as well. Can we know the PDF xk plus m if we only know xk and uk from k to k plus m minus 1. Okay? So we leave the unrealistic idea of knowing xk plus m exactly, and we then take the idea of knowing the PDF of xk plus m exactly. Okay? And the answer to this question is yes. And how can we know it? If I know these xk and if these input terms, these are just some deterministic quantities when I know them, and I always in the definition of a stochastic system I would always know the distribution of these noise terms. So you see that when I know this quantity and when I know this quantity, this xk plus m is just a function of these basic random variables. And as a result, from the distribution or from the PDF of these basic random variables, these process noise terms, I can calculate the PDF of xk plus m. So xk plus m is just a function of random variables here. When these are given, it is just a function of these random quantities, and from the distribution of these noise terms, I can actually calculate the distribution of xk plus m. So now let me try to write this. So we gave the answer yes to that question, and that means that we can calculate pxk plus m given these two pieces of information. Okay? xk, and I would have u k from k plus m minus 1. Okay? We can calculate this type of distribution or PDF. So this is called, in the system theoretic terminology, M-step transition PDF. Okay? And it is the generalization of the transition function to from the deterministic systems to the stochastic systems. So transition function in a stochastic system is not really useful for us because it takes the process noise realization as an input, which is never known. But the transition PDF, it really doesn't use the realization of the process noise, but it can use the PDF of the process noise terms, which is always available to us in the definition of a stochastic system. Therefore, this is what is useful to us in a stochastic system. That is knowing this is the counterpart of knowing xk plus m exactly in a deterministic system, from a deterministic system to a stochastic system. Okay? So here I have somehow obtained the counterpart of knowing xk plus m if I know these two quantities. And the counterpart is knowing the m-step transition PDF by knowing xk and uk from k to k plus m minus 1. Okay? Now I go to the second statement. Okay? What was the second statement? When we know xk and this, when I know this one and this one, the knowledge of the previous states and the previous inputs are not necessary for knowing xk plus m. Okay? Now I would like to generalize the same statement to a stochastic system. Okay? Now let me try to write the question related to that. Question. When we know the PDF of xk plus m, given, these are given here, given xk and u from k to k plus m minus 1, will the knowledge of the previous states x0 from 0 to k minus 1 and the previous inputs which are u from 0 to k minus 1 again, change this density. Or I can write just PDF. And that is my new question. In a deterministic system, I told you this. If I know these two quantities, the knowledge of previous states, x from 0 to k minus 1, and previous inputs, u from 0 to k minus 1, will not bring us any new information about xk plus m. Because I already know xk plus m perfectly when I know these two quantities. Therefore, these additional knowledge of the previous inputs and the previous states will not bring me any new information. So here we are asking the same question or a similar question, the counterpart of this property question in a stochastic system. Okay? If in addition to these state variables, if in addition to these known quantities, if I know the previous states and previous inputs, so if I add these quantities into the given condition, is this density going to change or it's going to remain the same? That is the counterpart of this property in a stochastic system. Okay? The knowledge of the previous states and the previous inputs if I add them into the given conditions in this distribution, in this PDF, will this density change or it's going to remain the same? If I want this type of property in the stochastic system, I don't want any change in this PDF when I add into the given conditions these previous states and the previous inputs. Okay? So now let us therefore rephrase this question here. In other words, do we have the equality that I would like to check here, P of xk plus m, given if I add xk these previous states as well. If I add xk, these previous states, x from 0 to k minus 1, that is going to give me just x from 0 to k. Because the addition of xk into this will make this x from 0 to k. Okay? X from 0 to k. And the addition of these previous inputs into this sequence will make this u from 0 to k plus m minus 1. U from 0 to k plus m minus 1. So this is the same density when I add this additional knowledge here into the given conditions. And I add the previous states and previous inputs to the given conditions here. Is this the same as, I put a question mark here, is this the same as this distribution? P xk plus m given just xk, u from k to k plus m minus 1. Okay? Do we have the equality given like this? If I have this equality, then this means that knowing the previous states and knowing the previous inputs will not bring us any new information. Because here you see that from the given conditions, I can remove these previous states and previous inputs. Okay? In that case, I will have the counterpart of the property, the second property of a deterministic system in the stochastic system. Okay? This type of property, this equality, is called the Markov property for stochastic systems with inputs. So this property, this is called the Markov property. For stochastic systems with input. Okay? So when I give you only the current state and the inputs between the current time and the future time, does this give me all of the information about xk plus m? Or adding the previous states and the previous inputs will bring me additional information into this PDF? Okay? If these two PDFs are equal, then we say that the system has the Markov property. Okay? And in general, we would really like such a property, because it makes the stochastic system in some way similar to a deterministic system. Okay? And if a system satisfies this type of property for all m, then we call that system, that stochastic system, a Markov stochastic system. All right? And if this equality is not satisfied for some m values, then of course m should be here for all m, which is greater than or equal to 0. Let us say greater than 0 in this case. Otherwise, the transition really is not meaningful. So for all m larger than 0, if I have this property, then the stochastic system is called a Markov system. And if for at least a single m value, if this equality does not hold, then we call the system a non-Markov system. Okay? Sometimes Markov systems are called Markovian systems, etc. And non-Markov systems would be called non-Markovian systems. So here this was my question, and we're going to see in these two lectures, that in this lecture and in the next lecture, this type of property is satisfied for a stochastic system if some assumptions are made. And the assumptions are going to be simple assumptions, especially if m is equal to 1, the assumption required for this equality to hold for m is equal to 1 is going to be very, very simple. But for m larger than 1, the assumption is going to be a little bit more complicated. And therefore, I'm going to be able to explain it not in the next lecture, but the one after that. So the answer of this question, if some assumptions are made, the equality is satisfied. So in general, a stochastic system does not have to be Markov. So this equality does not really have to be satisfied in a general stochastic system. But when we make some specific assumptions, we're going to see that this type of property can be satisfied. So now there is also the concept of being Markov for a sequence in stochastic processes is also similar. Okay? So this Markov name is coming from the literature of stochastic processes, and it is a similar property. So let us try to write its definition. A stochastic process, I will show this as Z0, Z1, going until infinity, is said to be Markovian. Is said to be Markovian. Or sometimes we call this type of systems a Markov chain. Okay? Is said to be Markovian or a Markov chain if and only if P of zk plus m given z from 0 to k is equal to P of zk plus m given zk. Okay? And this is true, let us say, for all m larger than 0. So in this case, you see that we are considering only a stochastic process, and there is no input here considered. Okay? So this type of definition, so this is the addition of, this is the condition required for stochastic systems with inputs. All right? On the other hand, in this case, there is just a stochastic process, and no inputs are defined. And we call a stochastic process Markovian or Markov, or we call it a Markov chain if this property is satisfied. So what is happening here? In the given condition, I have Z0, so let me write ZK minus 1 going until Z0 here on the left-hand side. And you see that I can, if this equality is satisfied, I can remove all of these past values of the sequence from my knowledge, from the given conditions here, okay? And this distribution becomes equal to this distribution, okay? So for a Markov chain, when I look at the distribution of a future state, if I give you only the current state, that is the most information that you can get. If you know additional previous states, they won't bring you any more information, okay? So I will write a theorem for Markov chains. Again, this is the case without any inputs, and I won't prove this. The proof is going to be in the notes actually, but I won't prove it in the lecture for not spending unnecessary time here. You can check the proof and make sure that you can actually do this type of probabilistic manipulations yourselves. So in this course, you're going to be required to be able to do such manipulations or derivations. So let us write the property of a Markov chain. For a Markov chain, the past and the future are conditionally independent. Given the present. What does this mean? In terms of probabilistic knowledge, this means the following. So I have the past, Z from 0 to K minus 1. This is the past of the Markov chain. And I have the future, K plus M to let us say here, I have from K plus 1 to K plus M. Okay? This is the future, this is the past. And suppose that ZK is given to us. Okay? When I give you ZK, and when I ask you the joint distribution of the past and the future, then you can be sure that for a Markov chain, these two are independent. Okay? So the knowledge of the present in a Markov chain makes the past and the present of the sequence independent from each other probabilistically. So I have Z0 from 0 to K minus 1, ZK, times P, Z from K plus 1 to K plus M, given ZK. Okay. So as I told you, I proved this in the notes, and try to do it yourself by using the conditional probability definitions, etc. for a mark. Of course, you will need to use this type of property here in the proof, because this is only true for Markov chains, okay? For Markov stochastic processes. So now I would like to give you some intuition about the Markov property. In order to be able to do such a thing, I will give you a stochastic system example, a very, very specific one, and it is actually the most common one that I use in my research. Okay? So suppose that you would like to model an object that actually flies with a constant velocity, or approximately constant velocity, let us say. Okay? So here I will call the position of the object as pk, and I would call the velocity of the object as vk. These are going to be discrete stochastic processes. Okay? And the object is also going to have acceleration, but these are going to be very, very small. Okay? So these are going to be close to 0. And I will model this AK as a stochastic process. And I would actually model it as a white stochastic process. Independent in time stochastic process. Okay? So here, instead of this AK, I can just say WK. This is going to be my process noise. Remember, I am trying to model the motion of an object which moves with approximately constant velocity. Okay? So let us try to, and suppose that the time interval between two discrete time instants is just K. Is just capital T. Okay? So that is my time step between two consecutive values of K. So now here let me try to write the state equations. So the position of the object at time K plus 1 is equal to position of the object at time K plus I would have velocity times the time interval. So I have T times Vk plus the acceleration of the object times T squared over 2. Okay? This is just some high school knowledge, I think. Just the kinematic equation for an object which has the velocity V and acceleration A. Okay? And I will also write the velocity equation. Remember, I want the velocity to be approximately constant. Okay? Vk plus 1, therefore, is going to be equal to Vk. But of course, object has a very small acceleration and white acceleration process. And I would therefore have this T times Ak. All right? So now let me define my state variables. So I would have the state xk, and this is going to be formed out of pk and vk here. All right? That is the definition of the state. And now I'm going to write the state equations. This is going to give me a linear stochastic process with actually no inputs, but with some process noise that is given by this acceleration. Okay? So I would have xk plus 1 is equal to, if I put here xk, and if I put here ak, this is going to be my process noise, and this is xk. So you see that the coefficients of pk and vk in the first equation is 1 and t. Coefficients of vk is 1 in the second equation, and the coefficient of pk in the second equation is 0. And the coefficients of ak here would be t squared over 2 and t. Okay? And here, what I would like to say is that ak is independent, identically distributed. So the the distribution of ak is the same for all ak values, and different ak values at different time instants are independent. In this case, I say that independence, sometimes it is said that ak is white. Okay? So whiteness comes from the frequency content of such stochastic processes, and it's not going to be really important for this course. So sometimes, instead of saying that ak is independent for all time instants, I might say ak is white. Okay? This is related to the frequency content of such a stochastic process, and it's not going to be important in this course. So let us say that ak is normal, 0, and sigma square. For all time instance, I have the same density. That means what identically distributed mean. So now I have such a process. Okay? Now I would like to concentrate the sequence pk, p0, p1, p2, going until infinity. Suppose that at some time we have pk plus 1. Okay? And this continues until infinity. Now I would like to check whether this pk sequence is Markov or not. Okay? If the sequence is Markov or not, pk sequence. Okay? So in order to be able to think about it, I will think about this distribution. pk plus 1 given pk. One-step transition distribution. Okay? Is this the same as the following distribution? pk plus 1 given p from 0 to k. Okay? I will ask this question to you. There are lots of p's, sorry, but I always call position as p. So if these two distributions are the same, then I can say that Markov property holds for m is equal to 1. Okay? This is like this property, but m is equal to 1 there. So such property should hold for all m, for all positive m, for pk to be Markov. But if this property, if this equality does not hold for m is equal to 1, then we are done. Such a sequence cannot be Markov. So now I want you to forget all of your probability knowledge, okay? And I want you to think about this problem, okay? What does this density represent? This is our knowledge of position at time k plus 1 given only the last position, okay? This is our position, the position of the object in the next time step given only the last position. Suppose that I have just, so this pk is just a point. I give you only this position. Suppose that we are in a two-dimensional space. I give you only this position and I ask you to predict me the next position. Okay? Just tell me what you know, or just tell me where do you expect the next position to be, given only this knowledge, pk, a single point in the position space. Okay? So here, when I think about such a problem, how can I predict the next position when I know only a single point in a space? So how can I predict the next position with this knowledge only? I don't know anything about the velocity of the object. So it can be anywhere, here, here, here. In the next time step, it can be anywhere, and it can be arbitrarily far, because I have no information whatsoever about the velocity of the object. Okay? So this is really a density with a very, very large variance or covariance, which is actually expanded or stretched over the position space. So not much is known in the given conditions of this distribution. Okay? The knowledge of pk really does not provide me much in the prediction of pk plus 1. Okay? What about the other case? In the other case, I am given this sequence. Let us say this is, I have again pk here. Okay? I have again pk, but this time, in addition to pk, I am given pk minus 1. And then I am given pk minus 2. And this continues until P0. Suppose that I have P0 here. Now if I want you to predict what Pk plus 1 is going to be, then you're going to be able to do much better. Okay? Why is that? Because if I know the consecutive position values, then I will have some knowledge from these consecutive positions. I will have some knowledge about the velocity of the object. Okay? So if you want me a prediction with this position history, I would give you somewhere here. So I would expect my Pk plus 1 somewhere here with some, if the acceleration noise has small variance, with some small variance. Okay? So my distribution is going to be concentrated around here and it's going to have small variance. But here, Pk can be anywhere. It can be arbitrarily far. It can be arbitrarily close. So I don't know anything about the velocity, and it can be in any direction. But here I have the direction information coming from these previous position values. So what can I say about this equality? Do you think I have equality for the positions? For the position random process, do you think I would have such an equality? These two distributions would be really quite different from each other. Okay, now I replaced the battery. So here we see that the position sequence is really not Markov. So what should I do in order to be able to obtain a Markov sequence here? And here I'm going to think about the following sequence. So I have P0 V0. And I have P1 V1 going until infinity. But what is this sequence? This sequence is nothing but x0, x1 going until infinity. Okay? So now let us intuitively think about this type of sequence. Okay? So now this sequence is, the distributions in this case are like this, xk plus 1. So I want you to predict the future velocity and the future position in this case. Xk plus 1, given I have xk, and I would have the other distribution, xk plus 1, given x0k. Okay? In one of them, only the current state is given. And in the second one, all of the previous states are given. Okay? Now I'm asking the question, is this equality, does this equality hold or not? All right? So now let us try to visualize this situation. Okay? In the first one, in the first distribution, I am given xk. What am I given? I am given the perfect knowledge of the position pk, and I am given the perfect knowledge of vk. Okay? And what do I want to do? I want to predict the future position and the future state. Sorry, future position and the future velocity. Okay? In the other case, I am given the current state, the current position and velocity. They are given to me exactly, but I am also given the past states as well. Xk minus 1, Pk minus 1, Vk minus 1. And here I'm here drawing them according to their positions. So but the velocities are also given. Xk minus 2 is equal to Pk minus 2, Vk minus 2, and so on. Okay? So here, what I want you to do is that you know the current position of the object, and you know the current velocity of the object exactly, with no approximation. You know them exactly, and I want you to predict the future, the one-step future, position and velocity. Okay? That is what this distribution intuitively is. And in the other one, in addition to the current state exactly, I give you the previous states exactly. Okay? So what do I need in order to be able to predict this distribution? Pxk plus 1 given xk. If I know the exact position and the velocity of the object, the current position and the velocity of the object, in order to be able to predict the position, here, Pk plus 1, I know this, I know this, I know these two quantities exactly, and the only thing that I don't know in order to be able to predict the next position is the process noise here. The acceleration here, I don't know. But I here know that acceleration is independently and identically distributed. So the only thing that I don't know is this Ak, and here, how can I predict this Ak? So the question is, do these previous state values, can these values bring me any additional information about this Ak? Okay? So we see that in order to be able to predict Pk plus 1, I need to know Pk, Vk, and I know them in both of the cases exactly. Okay? In both densities, I know xk exactly. So I know these two values. And in order for me to be able to predict Pk plus 1 for the next time instant, I need to know Ak as well. Okay? So the quality of my prediction depends on what I know about Ak. I have the same thing about the velocity. I know the current velocity. I know this exactly in both cases. The only thing that I don't know anything about is Ak. So my quality of prediction is determined by my knowledge, my amount of knowledge about this unknown Ak. Okay? And my question to you, here I don't have any additional information about Ak here, because I only know Pk and Vk, I know nothing else. Okay? But here, in this one, in addition to Pk and Vk, I know these previous state values. Okay? Do you think these previous state values would bring me some additional information about Ak compared to this case? Okay? Do you think the knowledge of these past state values will bring me anything, any information about this Ak? Because my quality of prediction is dependent on my knowledge, my amount of knowledge about this Ak, and therefore whether this equality holds or not is dependent on what these previous state values would tell me about Ak. Okay? So here I remind you the important thing. AK is an independent sequence of noises. Okay? So the past time instance might have some acceleration noise in them, but those acceleration noises are always independent from this AK. Okay? They won't tell me anything about the new value of AK here in these equations, because the noise sequence is independent in time. In every time instant, I would have a different noise realization of the acceleration here. So knowing the previous acceleration values won't tell me anything about the current value of AK, because of the independence of this process noise AK here. Independence of, or whiteness of the process noise here, whiteness of the acceleration sequence. As a result, my quality of prediction from here to here really will not change, because my quality of prediction, maybe the variance of these distributions, will not change, because here my quality of prediction is dependent on my AK knowledge, and these new information sources will not provide me any new information about AK because of the independence of the acceleration sequence. As a result, this equality would hold here. Okay? Because although I know more things here, they won't give me any extra knowledge other than PK and VK. They won't give me any information about AK here, these past state sequence values. That is why for this system, if I know the current position and velocity, I really do not have to know the previous position and velocities. For a constant velocity or nearly constant velocity object, the state sequence, position velocity sequence together at the same time is Markov. Okay? So the sequence xk, or let me write x0, x1, going until infinity is Markov. So in the past, it is sufficient for me only the latest state value, and the ones before that are not necessary for me at all. And here you see a very important thing. If I could tell you something about Markovness by looking at the process noise structure. Here, the process noise was white. It was independent for all time instants. Okay? And that was the cause of Markovianness here. That was the reason for the Markovianness of this sequence. If AK was not IID, if AK was not an independent sequence of accelerations, so if the accelerations in time were correlated, for example, if the object had almost constant acceleration in time, then this sequence would not be Markov either. Because in that case, these previous state values would give us some information about AK. Because you know that if I know these state sequences, I can extract some knowledge about the previous AK values. If the previous AK values are correlated with the current AK value, then that means that knowing the previous state values will bring me additional information. In that case, the equality would not be satisfied, and this xk sequence would not be Markov either. But since in this case I assumed AK was independent, I could say that this sequence was Markov. So Markovianness is really coming from the independence assumption there. It is going to be similar when we think about the general stochastic systems. If I assume all of the noises in time are independent, we are going to see that some form of Markovianness would be coming to our system. Okay? So in that case, if you have instead of a constant velocity object with the white acceleration noise here, if you had, for example, a constant acceleration object with white jerk, the derivative of acceleration is called jerk in the terminology, kinematics terminology. So if you had a constant acceleration object with white jerk sequence, in that case this model would have a 3 by 3 A matrix and state would be three-dimensional. It would also be including the acceleration of the object. In that case, position velocity sequence would not be Markovian, but the position velocity and acceleration sequence would be Markovian. Okay? So whatever is in the state, you need to give me all of them in order to be having the Markovianness here in the system. Okay? So this was some intuitive explanation. I hope I could actually explain it in a good way. If not, please ask me questions. So in the next lecture, we're going to look at this whiteness or independence assumptions, and we are going to see two system examples. The first system is going to have independent process noise, and the second system is going to have not independent but correlated process noise, and we are going to look at the Markovianness of both of the systems, and we will try to make a comparison. And afterwards, actually, we're going to make this whiteness assumption almost all the time, and then we will see that it is going to provide us with some Markovness property for our stochastic system. But that is going to be all for the current lecture. Thank you for watching. Bye-bye.